Okay, thank you, Simon, for the introduction. And I also feel very sorry I couldn't go because so many things come together. And, I get the short notice that this meeting finally will go in the middle of March. Then, it's very difficult to move things. But anyway, I think it will be, good opportunity to introduce my work. I know that a lot of people are study cold atom. Probably some, I think Simon studies Rydberg atoms. So in this talk, I will introduce our really recent work on Hilbert space fragmentation in driven dissipative Rydberg atom arrays. Okay, so in case you are not so familiar with the Rydberg atoms, so I first very briefly introduce the properties of Rydberg atoms. Right, so Rydberg atoms are no difference from the atoms that form ultra cold atom from Bose-Einstein condensates, right? So normally we use rubidium, cesium. Sometimes people use potassium, lithium, and so on. So when we excite the valence electron, the outermost electron, so this electron to some highly excited electronic state, whereas the principal quantum number n is much larger than 1, then we call this state the Rydberg state. Okay, so in Rydberg states, there are a lot of interesting properties, even from the atomic physics side. For example, the energy scales with n roughly inversely proportional n to the power of 2. So third L is a quantum defect because the electron will interact with the inner core electron and charges. So these mainly come from the quantum correlation between the valence electron and the inner electrons. And very important in Rydberg states, the lifetime is very long. So the lifetime is proportional to n to the power of 3. So for if your n is around 50 or even higher, you find the lifetime can be as long as 100 micrometer or even longer. So this will give us plenty of time to manipulate the Rydberg states before the Rydberg states decay. And also the size of the Rydberg cloud, okay, because highly excited, is proportional n to the power of 2. So this means when n is large, the size of the electron cloud is really huge. Typically, this can reach 100 nanometer when n is around 30. Okay, so sometimes if your n is 50, 60, you find the size of the Rydberg atom cloud, electron cloud can be the radius can be 1 micron. Okay, so because this electron is only weakly bound by the positive charge, so the electron has the Rydberg atom has very large polarizability. So typically this polarizability is proportional to n to the power of 7. Okay, so as a result, you find that due to this weakly bound property of the electron, so if you put two atoms together, they will interact. So there are two types of interaction. One is a dipole-dipole interaction that directly come if the two atoms maybe have a different parity, one S, one P, or one P, another one is in D state, so they will swap. This will lead to dipole-dipole interaction. The strength of the interaction is inversely proportional to n to the power of 4. That means if we have higher Rydberg states, the interaction will be stronger. There is also the van der Waals interaction. So this van der Waals interaction pretty much comes from the second order perturbation of the dipole-dipole interaction. So the van der Waals interaction has a very different scaling with the principal quantum number. That is n to the power of 11. So you can imagine that if we increase the n to a relatively large, so even when the atom is several micrometers, the interaction can be the range, megahertz to gigahertz. So this is some relatively old, also new experiment about 13 years ago by Anton Brown-Yeh's group in Paris. So they measured the van der Waals interaction in D state. So you can see that. For 53D, for example, around 3.5 microns, the interaction is about 10 megahertz. For 82D, so you see that it is around 8, 9 micrometers. So there the interaction is 10 megahertz. Because normally the excitation laser Rabi frequency is in the order of megahertz. So this means that the interaction can dominate the dynamics. So now, depend on the distance, we can control the interaction. When the interaction is smaller than the Rabi frequency, so you see that the two atoms can be excited from ground state to the Rydberg state, right? So this shows a double excitation possibility as a function of time. When you increase the Rydberg interaction by putting them closer and closer, so in this case we have a distance 4 microns, so the interaction is 7 megahertz. So in this case, you see that the double excitation is completely suppressed. So this leads to the so-called Rydberg blockade. So as a result, what we found is that now if we have a gas, the picture here is if you have a gas, depending on how dense the gas is and what will be the Rydberg state. If the Rydberg blockade is not so important, what you see is a lot of interesting atomic physics. For example, the Landau-Zener transition, the Stark effect, and so on. And if we increase the interaction, so because now the blockade will kick in such that the excitation, laser excitation will compete with the Rydberg interaction. So even in a gas, we could have some crystallization of the Rydberg excitation. So the left figure is the prediction Thomas Paul predicted, about 15, 16 years ago. Then later on, so this is observation in a lattice gas, in a optical lattice. So they really see this regular structure of the Rydberg excitations. And now if we even have even higher density, what will happen is that one ground state atom can enter the cloud, because the cloud of the Rydberg cloud is so big. So this ground state atom can enter. So the green dots is ground state atom. So this will interact with the Rydberg electron, because this is a polarization interaction and electron atom interaction is attractive. So this will produce these oscillatory potential waves, and this ground state atom can be trapped here. So depending on the angular momentum, we have different shape of molecule. So here, this is a so-called ultra long range molecule, because as I said, the Rydberg atom is so big, right, 100 nanometer or even larger. So you find that this molecule is also big, right? So it's a very large molecule. And of course, in recent years, we all see that there is a very rapidly growing area that is put atoms, Rydberg atoms, in optical array. So this is in one of Lukin's group experiments. So they show that you can, for example, create a square lattice, or you create a triangular lattice. And when you do the Rydberg excitation, you can have a large ensemble of Rydberg blockade here. So this green dot is ground state atom, and the red dots are Rydberg atoms. So you see that they form this kind of perfect lattice of this geometry. So not only about this square lattice and the triangular lattice. So essentially, depend on the system and the aim, so we can have different type of the geometry, and also depend on the Rydberg states. If you have a ground state coupled to a single Rydberg state, or you have two Rydberg states, so we can have a lot of different physics and different many-body models. So if there's only van der Waals interactions, we will have Ising like a many-body model. If you have two Rydberg states, one S, one P, for example, coupled by microwave, so this will lead to spin XY model. Then, of course, we can also now, depend on the geometry, we can even realize some topological model like the famous SSH model. So this is some introduction. So now in the following, I will focus on the strong van der Waals interaction. So in case of the strong van der Waals interaction, what will happen is that when the dipole blockade dominates, so this will lead to some dynamical constraint. Okay, so in this case, what will happen is that so we find that the nearest neighbor interaction can affect the Rydberg excitation, such that the atom can be excited, one atom in the middle can be excited only when two neighboring atoms are in the ground state. So the p operator is a projection operator to the ground states. And typically we find that this longer range interaction is not so important. So here, about 15 years ago, Igor Lesenovsky started that, okay, for this model there is a very interesting dimer state. So this this pink shows that there within this configuration there's only one atom can be excited. But normally the dynamics, the ground state is difficult to achieve, but dynamically you find that especially for Rydberg atom, we can observe dynamics quite conveniently. So due to these dynamical constraints, that is, so the green atom in the ground state can only be excited if the two neighbor is also in the ground state. But if one of the neighbor is in Rydberg state, so such process is blocking. So this leads to the so-called many body scar and PXP model. So here we find that if you start with this so-called Z2 configuration, that is one atom in ground state, one atom in the Rydberg state. So this will only cover a finite number of possible bases. Okay, so this possible bases roughly you can see is marked by the this cross. So these are the eigenstates that this computational basis can explore. As a result, so the dynamics, eventually the dynamics will not thermal. But the PX model, if you look at the PX model, look at the level statistics, you find it shows quantum chaos. However, if you start with this particular, this basis, so what will happen is that the dynamics will only, evolve in this many body scarce state such that it will not thermalize. And this has been also observed by Lukin's group about about 9 years ago. It's so fast developed. This field developed so fast. So this is roughly this is the initial state, right? So you have one at the yellow means there's one Rydberg, the dark means ground atom. So you see you have a number of Rydberg atoms. And in between the ground atoms, starting from here, we find the dynamics will repeat. So this shows revival dynamics. So the system will not thermalize because of the many body scars. And if we look at from the theoretical point of view, if you look at the the total Hilbert space, or right, so we find that there is a large thermal bus and there is a small sector where that sits the so-called quantum many-body scar. So the dynamics in this region will not thermalize. And as I said, so fundamentally, so the PXP model, supports the so-called dimer. If we look at the dimer, according one dimer, zero, so zero dimer, so the quantum many-body scar corresponds to zero dimer states. And if we also have a one dimer, two dimer, if we separate the total Hilbert space according to the dimers, we have L different blocks. So the L is the total number of the sides. And in fact, so in this PXP model, there is a hidden symmetry. Okay, there's a hidden symmetry. And according to this hidden symmetry, what we can do is if we can, if we can even further separate, these dimers into exponentially large number of subspaces. And when this block, the number of blocks is exponentially large, so the L is the total number of the system size. So this corresponds to a so-called Hilbert space fragmentation. But in practice, since this Hilbert space fragmentation is hidden, it becomes difficult to observe this. So as a result, so here I show some simulation. I start this there I consider 6 atoms, so there are in total 64 computational bases that I consider individual computational bases as my initial state. So I do the simulation. So you see that the dynamics is kind of mixed together because so this shows the total magnetization. So you see that depending on some states, they more or less stay as the initial state. Those they form the so-called frozen states. So some are relatively simple, so only a few states will oscillate. But for a lot of basis states, you find that they just mix together, and the dynamic looks quite chaotic. So then the aim of this work is, we want to study how we can, find the operator to distinguish the hidden space, hidden subspace, and also find a model to, observe this Hilbert space fragmentation. So this comes to the contents of my talk. So we started the Rydberg atom, and we consider open quantum system. We add a local defacing. Okay, so then in this system, we show that the Hilbert space will emerge, and we find the effective defacing PXG model, and we find that the Hilbert space fragmentation corresponds to the degenerate zero modes or the stationary states. For the defacing PXG model, there are multiple zero modes. And we can also find the operator to identify the symmetry, find the individual, zero mode or the individual space. And eventually we find the scaling of the fragmented Hilbert space analytically, and indeed it is exponentially scales with the system size. Okay, so now let's come to the system. So our system is a chain of Rydberg atom coupled by laser, resonantly coupled by laser. And so in Rydberg state, so there is this defacing. So the system is described by this mass equation. So this is Hamiltonian. We consider delta is zero, and this is defacing operator. So the Q project to the Rydberg states. Okay, so now if we solve the dynamics, similar the story, we start with the computational basis and we solve the dynamics. When we plot the magnetization, we find that in the intermediate time scale, there is a metastable regime where dynamics almost doesn't change. Okay, doesn't change. In fact, the fragmentation takes place in this region. And similarly, if we look at purities, we see that in this metastable regime, the dynamic doesn't change, for quite a long time. This is universal. If we look at a different system, size 7, 8, 9 particles, we all saw these similar structures. Okay. So what we can, so because the original Hamiltonian is relatively complicated, and we consider this in a strong interaction regime. So what we do is we use a unitary transmission, using the interaction two-body interaction, make a unitary transmission. Then we will find that this will lead to an effective defacing PXP model. Defacing PXP model. Okay, so this transmission will not affect the defacing part because this Q and this Q commute. It only affects the effective Hamiltonian, right? So the original Hamiltonian has the laser coupling and the interaction. So in the rotated frames, we only have the PXP model. Now, if we diagonalize this master equation, so we will find all these spectra, and so the stationary states, or in other words, the eigenvalues that the real part is zero. There are a lot of degenerate modes. So this is in the circular region. If we look at here, we find that we have a number of degenerate modes. And if we look at the individual degenerate mode, we find that they form this block. So this is not cartoon picture. This is a real eigenmodes from this this individual degenerate mode. So each block corresponds to one of the degenerate mode. Okay, and in fact, the largest degenerate mode corresponds to the quantum many-body stars. Because in fact, here the quantum many-body star has only one space, so there is no degeneracy. If you look at other space, for example, if there dimer is 1 or 2, so there are 2 possibilities. So we find that this degeneracy now split. Okay. So we want to understand how this, or we distinguish how we can split these individual subspace and how the degeneracy splits. Okay, so this is before we look at some analytical results. So this is we also calculate dynamics using the effective model. So you see that in the stationary state, so dynamics doesn't change, and in fact these curves will overlap with the metastable value in the original model. Later I'll have some comparison. So what we do is we first construct a consecutive double excitation addressing operator, that is A. So compared to the dimer operator, what we do is we add a 2J for this dimer. So essentially it's add some address to the where the dimer sits. And with this, we find that this operator commute with the PIP model and also commute with every defacing operator in the master equation, because we have a local defacing, we have the L individual defacing operators. So this gives us a strong symmetry. And with this, so we can already find the interesting property. For example, for the quantum many bodies scar subspace, we find that the corresponding mean value of this A is 0. Okay. And because this A commute with the PIP model and also individual defacing operator, this gives us so this means that this is a strong symmetry operator of the the value of the system. And then what we do is we can construct all these individual subspace using the consecutive double excitation addressing operator through the so-called commutant algebra. We can find all the 0 modes. Okay, so this is what we can find by applying this operator to individual bases. We can find all of these bases. So we find so this is as I said before. So for the many body scar space, there is only one. So there is only this one basis state possible subspace. However, for single dimer subspace, we found two degeneracy split. Okay, degenerate space, and for 3, this is the 4. We find that the degeneracy are all separated from here. And very importantly, we find that for different 0 mode or different subspace, the corresponding value, the eigenvalue of the A operator are completely different. For example, in this many body scar, so this is 0. So here we find that for the dimer of single dimer space, one eigenvalue is 2, another is 32, and 3 we have 8. And so you see that in this column, all of these values are different. However, if you look at the magnetization, for example, the single dimer space will have a 0, right? So and here we see that they have these 4 dimer states. There are 2 possible values. So this magnetization cannot distinguish, but the A operator can distinguish the subspaces. And also what we also do is by counting what are the possible configurations of the this subspace, we find that the total number of the 0 modes or the total number of the blocks is given by a recursive relationship. So this L is the number of sites. L is the number of sites, right? So depend on FL minus 1 plus FL minus 2 plus FL minus 4. And there are this initial value. So with this, as long as I have L, I can get the total number of the possible 0 modes or the number of subspaces. And when L is large, we can get analytically, we can get a scaling relation. So here A1 is about 0.7, alpha is 1.75. The total, remember the total number of bases is 2 to the power of L, right? So now we find that the number of subspaces is about 1.75 to the power of L. It's exponentially large with L, but still much smaller than the total number of the Hilbert space. So this shows that these sub blocks really form a Hilbert space fragmentation. So this is the comparison of the numerical simulation and the analytical calculation, and also compare with the total number of the Hilbert space. So this square denotes the total number of Hilbert space as a function of L, and this line is the scaling A1 times alpha to the power of L, and the dots are the coming from the recursive relationship. So this square is the number of Fibonacci number. So number of the Fibonacci number gives the number of bases in the quantum many-body scar state. It's also exponentially large, but it's much smaller than the total subspaces. Okay, so now this is some comparison. So fine, I think this is my last slide, so, almost last slide. So I compare this, with so this is Rydberg, atom model. So here we show that in the metastable region we have, this Hilbert space fragmentation, and if we compare this value, so the lower row is the diffusion PQ model. If we compare this value, we'll find that this value match the metastable region for quite a long time. Okay, so this now if we look at the zero mode in the Rydberg atom model and the diffusion peak model. So we put all of this zero mode here. So this red circle are the diffusion peak model. So we see that the real part of the eigenvalue are zero. However, for the Rydberg atom model, we find that there is one true zero mode, but there are a lot of quasi-degenerate modes. So remember, look at here. So this separation is much smaller. Okay, so much smaller. So the energy scale is in terms of gamma. Gamma is the diffusion rate. So it's about uh, 1,000th or 100th of the gamma decay rate. So in fact, here we can all, if we look at here very carefully, so this because this mode in the Rydberg atom model, this mode in fact roughly determine how long this plateau will be, because at some point, since the Rydberg atom only have one unique stationary state, so at a very long time, so all these plateau will merge together, form this unique stationary state. So this mode, in fact, determines roughly the lifetime of this planet, how long it is. We develop a mean field, so this is very simple. You assume every atom is identical, and we can calculate the diffusion rate of this system. So that is given by omega squared divided by v squared times gamma. That is the effective diffusion rate. So here is given by this dashed line. Then we can look at what is this mode. Okay, the real part of the lowest the first exciting mode. So this is as a function of the system length, because we have diagonalized, we cannot do very large system. We diagonalize up to 13 atoms. So we find that there is a trend that this mode gradually approaching to the mean field prediction. I mean, this is good because from here we can, we can estimate how long, if we really do the experiment, how long the time we will need. Even we do not want to, diagonalize or our system too big, we cannot diagonalize to find the eigenvalues. Okay, so with that, I want to make a quick conclusion of my talk. So in this work, we started the dissipative Hilbert space fragmentation in a strongly interacting Rydberg atoms. We found that the clustering of the observables is an indication of the Hilbert space fragmentation. Then we develop a effective diffusion peak model to explain, to capture the physics. So in the diffusion peak model, the degenerate zero mode corresponds to the fragmented Hilbert space, and very important, we use a double excited addressing operator to identify the symmetry and find the subspace analytically. And we can show that the number of the zero mode grow exponentially with the system size. With that, I want to thank you for your attention.
Thank you very much. We have time for questions. Could I just ask a little bit about the dephasing? I mean, the rate you put in, is that derived from experiments? Is it associated with laser phase noise or something like that?
Yeah. So mainly we assume that here this diffusion comes from the laser diffusion noise, because I mean, if you have a gas, maybe the motional can also cause diffusion, but since we are in an array, optical array, so we assume that this diffusion comes from the laser noise.
Okay, yeah. But even in the array, the motion of the atoms, because they're not necessarily cooled to the motional ground state, does that play a role as well?
No, this will not play a role. In fact, so you find that as long as the so the only requirement is that the nearest neighbor interaction is strong enough. So even, for example, two atoms separated slightly away from their center of the trap, as long as this interaction is much stronger than omega, it still works. And the longer range interaction, so the tails of the van der Waals interaction will not affect the dynamics as well.
Okay, good.
It's quite a robust system.
Good. Other questions? I don't see any, so let's thank Weibin again for a very nice talk.
Thank you.